All right, so we're going to consider one last measure of importance. Okay, and this one in many ways is maybe even more, maybe even is the most useful. Okay, so so basically, so the measures that we were looking at previously, okay, the omission and the minimal depth, they're nice, but they don't really tell us the marginal effect of the variable, right? They're not completely analogous to the regression table, right? Because, for example, when we were looking at, so we saw, for example, that those variables thought that they usually thought that the living area of a house or the number of bathrooms was very important. But that doesn't tell us, first of all, it doesn't tell us the direction of the effect, right? So it doesn't tell us that, okay, is a bigger living area conducive to a more expensive house, or is a smaller living area conducive to a more expensive house? Okay, so it doesn't tell us whether the effect is positive or negative. It just tells us that that particular factor is important in some way. Another thing that it doesn't tell us is the size of the effect, right? So it doesn't tell us the direction, but also doesn't tell us the size. So if I were to go from having, let's say, a house with 2 bathrooms to a house with 3 bathrooms, or if I were to go from, a house that has a living area of, I don't know, 2,000 square feet to 3,000 square feet, what would the actual effect be on the price of the house? Those measures that we just considered don't really say anything about that. Okay, so the final way of measuring the importance of a variable then is to compute the partial effect. And we've explored this a little bit before. Okay, we've created those partial dependency plots for the OLS model, and we're actually going to do the exact same thing for the random forest model. As it turns out, that function we were using, the PDP function, it can handle not only OLS, but it can handle a random forest model as well. Okay. Now, for today, okay, I'm not going to go into sort of all of the gritty details about how these partial dependencies are computed. I think I want to save that for a later class where we can really sort of dig into some of these details. Okay. For now, we're simply going to learn how to use the function. Okay, and we're going to learn what kind of output it can produce. Okay, so let's go into R here, and okay, you can see. So I need to load up this PDP package. Install it if you don't have it installed. Okay, and I'm going to compute the partial dependence of this model, and this can sometimes take a little while to run too. Okay, so let's run this. Okay, actually, it was pretty fast. Okay, and okay, so let's have a look at this here. Okay, so what this is showing you is the predicted value of the home based on the number of bedrooms according to our random forest model. So you can see it's kind of interesting. The effect is nonlinear, and this is what we were thinking last time, right? The regression model, as you recall, estimated a negative effect for the number of bedrooms, and we were thinking that that was perhaps because of the interaction of this with the distance to the city or something like that. Okay, well, so we can actually see that nonlinear effect here in our partial dependence plot. Okay, so you can see the predicted price of the home actually is minimized at 3 bedrooms, and then it recovers after that as you go to 4, 5, and 6 bedrooms. Okay. Now you can have this graph. Okay, you can also look at the table corresponding to the graph. Okay. The only difference there is, so by the way, I didn't really explain this command, but it's the same command as before. Okay. So we call the function partial. The first argument here is we call it on our model, so the random forest model. We have to tell it some data to use, so I'm using the test set, okay, to make our predictions. We tell it the variable that we're interested in this case it's bedrooms. Notice it has to be in quotes. And then I put plot equals true. Okay. Now if we don't put plot equals true, it's going to give us the same information as this plot, but in the form of a table. Okay. Now compare this with what I get when I call this same function on OLS. Okay, as you'll recall, OLS will always generate a linear partial effect because OLS is a linear model. Okay, so this graph that we saw earlier, this graph, okay, is the closest thing to a regression table that we can really get with random forest. Okay, because you see, when we're dealing with something that has a nonlinear effect, the marginal effect, or what happens when you increase the variable by 1, changes depending on the value of the variable and potentially the value of the other variables in the data. Okay, so in other words, so we haven't quite gotten to the point where we actually have a table just like a regression, but we can't really expect to have that, okay? Because you see, in a regression, right, what does this table answer? So this table answers what is the effect of increasing the variable by 1 on the dependent variable, okay? So if we have a linear model, that question makes sense, right? So if I go back to my graph here, if we have a linear model, right, then the effect of increasing my independent variable by 1, the effect of increasing, the number of bedrooms by 1, it's always going to be the same value because this line has the same slope. Okay, so if I increase it from 1 to 2 bedrooms, it's going to fall by a certain amount, and it's going to fall by that same amount as if I increase it from 5 to 6 bedrooms. Okay, so talking about a single marginal effect makes sense when the model is linear. But if you have a more accurate, if you have a more sophisticated model that's nonlinear, like random forest, well, the answer to that question of what happens when I increase by 1 bedroom, it depends how many bedrooms you have in the first place. Okay, so you can see here, for example, the effect of increasing from 1 to 2 bedrooms is negative, whereas the impact of increasing from 3 to 4 bedrooms is positive. Okay, so I hope that makes sense. Okay, so this graph here is the sort of the closest that you're really going to come to understanding or to having a marginal effect, kind of like the table that we had for the regular regressions. Okay, but you shouldn't think of this as a weakness. You shouldn't think of the lack of a table like that as a weakness at all. Okay, the strength of this model is that it doesn't estimate just a single marginal effect for the variable. This model actually understands, okay, well, that effect is going to vary depending on where I'm currently standing. Okay. Okay. All right, so I hope that makes sense. Okay, and then the last video is just going to discuss what I want y'all to do for homework.